Yes, okay. So welcome to the external synergy session. So first of all, before we start, I remind you we have a code of conduct, so please behave respectfully of the others. And this is also an hybrid meeting, so there are people online. So before asking any question, wait for us to bring you the microphone. So the first speaker of the session is Charlotte Ward, who's also chairing the session together with me. So Charlotte, go to class.
All right, great. Hopefully this microphone is working as well. All right. Yeah, thanks everyone for coming. I'll be talking a bit about our work to do pixel level joint analysis of data from the Rubin and Euclid surveys. But I wanted to emphasize from the beginning that the methods that we've developed for the joint Rubin-Euclid analysis go for any survey. So they can also be applied to Roman and any other complementary or synergistic data you have with Rubin. So please keep that in mind. Okay, so the goals of this work have really been to combine the advantages of Rubin, which provides us with really deep optical photometry, and Euclid, which doesn't go as deep, but surveys the sky at really high resolutions. So in the plots here, you can see that we have a lot of nice overlap between the Rubin field of view and the Euclid fields shown on the top left. We can get optical and near infrared coverage when we compare SEVs across the full bands. And in particular, we can see in the plots at the bottom that Rubin on the left goes very deep, but we have blurring from the atmosphere, whereas Euclid might not go as deep, but provides us with this really nice high resolution information from space. We're also really interested in facilitating transient science with this work. In particular, we want to be able to produce light curves across both surveys, particularly in the deep drilling fields. We want to do detailed analysis of host galaxies in order to, for example, calibrate local environments for 1A supernovae, and to study host galaxy properties of various classes of transients. And we want to have ways to get precise transient positions and host properties. And the reason that this is important for Rubin is that as we get to the depths of Rubin, shown up until the third plot on the figure here, is that we reach a point where we're so deep that a large fraction of galaxies are blended with other galaxies, and this can cause inaccuracies in photometry. We can miss faint background sources. So we really want to leverage Euclid in order to come up with accurate galaxy catalogs that capture all of those faint background sources and extract accurate photometry. So this resulted in this effort to do the Euclid-Rubin derived data products. And the idea was to have multiple releases that became increasingly complex and more sophisticated over time. And I'm showing on the bottom here a plot from Irfan, who has been working on the second level of this processing, where we can see why we might want to do this. So on the top is showing a particular source. The region that it's detected in Rubin is shown in green, and the footprint that it's detected in Euclid is shown in purple. And this is a simple case because we have a one-to-one source mapping. But on the bottom, we can see here that in this orange region, that's the area where Rubin detects one source. But in Euclid, we have two separate sources. There's 1 and 2. And we really need Euclid's information to see, okay, there are two sources here. How do we now extract better quality Rubin photometry with that information? So I've been working on the DDP3 level, so the more advanced, slower level, that is kind of one of the long-term goals of this work. So the idea here is that we do full joint pixel processing of data from Rubin and Euclid at the same time. We have a model for the observations and their properties, including their point spread function, their WCS, as well as the sources within the observations, and we model them simultaneously through this framework. And in the era of Euclid, for example, this is becoming increasingly more complex compared to similar efforts in the past, because at space-based resolutions, you start to really see that galaxy profiles are very complex. We can't just assume they all have a simple profile. So we therefore need to have a way to treat these complex galaxy profiles, and we can achieve that using neural network-based priors on galaxy morphologies. And also at the depths of these surveys, we need this code to be fast. So it needs to be GPU accelerated and needs to be able to run efficiently across thousands of epochs for the transient science cases. So this is the code that we've built for this joint Euclid-Rubin analysis effort, but can be applied to any survey data. It's called Scarlet 2. You can check out the documentation here. And it's sort of built to deal with these challenges that we have when we have wide survey data from space as well as ground. And as I mentioned, it has a number of features that I'll go through quickly, but you can feel free to ask me if you have any questions. We have these priors on galaxy morphology that help to stabilize the fitting in very blended situations. We have wavelet-based source detection in order to be able to model these complex structures like the one shown here when we have multiple sources and low surface brightness galaxies. And we also are able to model galaxies as well as transients across multi-epoch imaging and extract high-quality light curves, which we've shown with LSST sims as well as real data sets. But now onto the processing that we're doing with Rubin and Euclid. So in order to validate the pipeline that we've built, we've been using the open universe simulations. And there's been a Euclid component to these, led by Axel Greener and Rachel Mandelbaum. So we've used that in addition to the public open universe sims. And I've shown here just an example of a run on a subset of a coad where we're modeling the Euclid viz and Rubin images at the same time and testing how well the deep blending and photometry works. And for this work, we're really focusing on the blends. So where we have lots of galaxies overlapping each other, that's where the joint processing analysis of both Euclid and Rubin together is the most powerful. So we're analyzing the performance in these very blended situations to show that we can improve the pipeline outputs when we do this joint analysis compared to just one survey at a time. So Euclid Rubin DDP3 pipeline does. So we take our Euclid images, our Rubin images, we resample them to the same highest resolution world coordinate system. And because that resampling can produce extra correlated noise, we measure the power spectrum of that, incorporate it in the fitting. We then do our wavelet-based source detection and initialize the sources using those shapes, but also make sure that we didn't miss any sources in the input Rubin and Euclid catalogs that were made separately. We then simultaneously, across all of that data, fit the galaxy SEDs, the morphologies, and the astrometric shifts, which has turned out to be very important. And then because we're using these non-parametric galaxy morphology models with positive constraints, we have another set of calibrations we need to do relating to bias factors introduced by that. So we use the new footprint information and those bias factors to get the end photometry. But the goal here is to be running it on the real Euclid and Rubin data. So we've been validating this pipeline on Euclid Q1 and Rubin DP1 data. I've shown here as an example a supernova host galaxy where we're modeling across Euclid Viz, Euclid NIR, and Rubin G bands. I've just shown a subset of them, 3 of them here, where we're modeling these galaxies together. And just to illustrate why we want to do this, this is kind of comparing a Rubin-only run with a Rubin and Euclid joint run. And you can see the same sources are in the row above and the row below. And for some of these complex galaxy morphologies, we really benefit from using that Euclid morphology model to anchor the Rubin photometry. And we've also been looking at some supernova host galaxies that were found in the early data and looking at how the output SEDs of this pipeline compare to the catalog SEDs. And this is just showing some of those morphology models as well. So we really want to validate this pipeline by using it for early science. That's really where we'll stress test it in difficult situations. So we've been doing that in a number of different science cases and with a number of collaborators. Just to go through some examples, we've been looking at how we can use the joint Rubin Euclid analysis methods and data to analyze different populations of AGN. I'll draw your attention to some talks in the AGN science session where we have presentations on looking at the host galaxies of changing look AGN, on looking for wandering massive black holes identifiable either as offset tidal disruption events or AGN, where we really need to have a good morphology model of the interior of the galaxy across many bands. And we also want to be able to use this approach to make multi-survey light curves. So for example, Miranda will talk later today about our plans for looking at change and look AGN with this approach. But I also wanted to point out some other cases where this has been really powerful for early science. So this is a supernova, which is published in the paper cited at the bottom. But we were interested in this because the Rubin photometry and the early difference imaging suggested that there could have been some early detections before the supernova went off. And if you looked at the difference imaging, this, I think, suffered from an astrometric mismatch. So we had this dipole in the photometry. So we weren't sure if we could trust this, but it would have been really interesting if it were real. So then Kendall somewhere here. Yes, Kendall. Then took the cutouts from the brokers and then reprocessed them with Scarlet 2, redoing that astrometric shift fitting, and found that those detections were real at almost the 5 sigma level, not quite. So this is kind of the case where rerunning this pipeline allows you to do a full scene model across the images that you have, remake photometry, and have an independent pipeline verification. This was also demonstrated, in the early, with the Zwicky transient facility, in particular, looking for tidal disruption events that were non-nuclear. The ZTF image is shown above here, but this tidal disruption event was a bit weird. It suggested it had a 1 arcsecond offset to its host nucleus. This modeling approach run on the ZTF imaging confirmed the offset, and HST follow-up confirmed what we found statistically. So this could be really useful for looking for unusual nuclear, but not quite nuclear transients in the era of Rubin. And we're also using it to do deblending when we have situations where we have multiple transients overlapping each other. And this is particularly important for the lens supernovae, where we expect that a large fraction of lens supernovae will be quite blended in the Rubin imaging. So I'll refer you to the lensing session where Vina Krishnaraj will talk about what we're doing with a pipeline to extract deblended photometry and host models across all Rubin imaging, as well as any complementary space-based imaging or ground-based adaptive optics that you might have in order to extract the best quality possible light curves. And I wanted to mention briefly some work that's going on in the LSST desk pixels to light curves working group, where we're validating this kind of approach of scene modeling with a few different codes, including Scarlet 2, in order to extract high quality supernova 1A light curves, where we're rerunning photometry of all the dark energy survey supernovae, comparing them to the previous pipeline, and showing that we can run this code that's built for the joint analysis at scale in order to extract high quality supernova light curves with this different approach. And I wanted to point out that if you're interested to run Scholar 2 on the Rubin Science platform for your science, please come and chat to me and I can tell you how to get started. So with that, I'll leave up summary. I just wanted to summarize by saying that we think that we can really do well if we combine the strengths of Euclid's high resolution and Rubin's depth in this joint processing approach. We've built the code to do it, and we're now testing the pipelines on the real and the simulated data. And we're also trying it out on a number of different science cases. If you have any thoughts on other science cases this could benefit, or what you would like to see from the level 3 joint release of this Rubin Euclid derived data products, please let me know, and I would love to chat to you further. Thank you.
Thank you, Charlotte. We have time for one question.
This is kind of a naive question, but for the cases of where you have like time domain phenomena, how often will you have contemporaneous Rubin, Roman, or Euclid coverage?
Oh yes. So we'll have a lot of situations where in the Euclid wide survey, we just have a single epoch, a single coad. So we'll often be in situations where we'll have a nice Euclid image of the host, but not detailed photometry. So you can use it to anchor your model across the multiple surveys, but it's really only the deep drilling fields where we'll have good light curves across both. For Roman, it's a little bit better. So we'll should have pretty good time domain photometry in some of those fields. But yeah, the goal here was kind of that, we'll have very mismatched overlap depending on which part of the sky we're looking at. So it could be Euclid Rubin, it could be Roman Rubin, it could be something else depending on what's available. And we hope that it will be very general for what data people have.
Thank you very much. Let's thank our speaker again. So, next speaker, Anand Rachor. I hope I pronounce it correctly. Yeah. Okay, we'll talk about multi-band photometry for the Euclid Rubin.
Okay, thanks. Hi all, thanks. My name is Anand Rachor, so I'm going to talk to you, so something kind of related, but just talked about. So it's about the multi-band photometry. So on the Euclid side, how you do the phosphotometry on the Rubin imaging. So this is called the derived data product framework that Charlotte mentioned. And this work is led by two groups. So one led by Simone Anet, who's here in France, and another one led by John Moore in Germany. Let's have some other people here. So just, I thought I would make a very quick introduction, reminder of what Euclid is. So it's a satellite launched 3 years ago. Its characteristic are a large field of view. You can see like about 100 times the one of Hubble. So on a sharp PSF from space-based imaging. It has 3 instruments, two imagers, the VIS, which is a broad, large band in optical, and 3 near, which will have 3 bands in near infrared, and then a Grayson spectroscopic instrument. And so the goal of Euclid is to constrain dark energy using 2 primary probes, weak lensing, and bioacoustic oscillations with measuring redshift from the Grayson. And to do that, so Euclid will do a wide survey, so about 1/3 of the sky. It started in February 24, and it will last 6 years. So you can see here the footprints, well, the values of the 3 data releases from DR1, 2, and 3. So DR1 is already released internally and should be public soon in 2 stages in a few months. And and you can see also the deep fields of Euclid. Okay, so the reasons that Euclid needs, so for weak lensing, so Euclid needs good photometric redshift, as you know, because you need to, it's key to split your, for instance, your source samples in redshift tomographic pins, as you can see on the left. And to do that, Euclid alone cannot disentangle really have good photometric redshifts because it has only this large broadband in the optical photometry. So by design, Euclid needs complementary optical, multiband optical photometry. And so it is done, so the way it is done that in the northern sky, it will use a Union survey, which is a survey built with 3 observatories, Subaru, CFHT, and Pan-STARRS. And in the south, it will use Rubin, LSST. And you can see the Rubin footprint here. So it's a large fraction of the Euclid footprint, and you can see the Rubin deep fields also. So the Euclid deep field south also is special. Like there will be for sharing of data. And so here just reminding that so far, so for the DR1, Euclid has used a DS data, which is shallower. So we expect that Rubin will bring a significant improvement here. So with 1 magnitude deeper photometry and addition of U-band, which helps break the degeneracies. So it will be great for Euclid. And to do that, so how do you share data between 2 large collaborations? So there's been a lot of work done to do that, to maximize the science of sharing the data and to protect each science case from each collaboration. So this is called the derived data product approach, so this framework. And so this Guy et al. Paper describes all those products that have been identified, so with input from the community to consortia. So there's tens of products for science-specific case. So if you can look into that paper to see your favorite science case, if what's in there. And then few of them have been identified like cross-cutting, so large science case would be also for benefit for large science. And so the DDP2 is simplest one. It says just to do phosphotometry. So you are in one survey and you do phosphotometry from the imaging on the imaging of the other survey. DDP3, what Charlotte just described, is to do something more complex, to do the deblending using information from both surveys. And then you have the DDP4, which is compute photometric redshift from both from the pixels themselves. And so as you may have guessed, so from at least for DDP2s, in each collaboration, there'll be a specific group. So from the Euclid side, so we'll do DDP2, Euclid, start working on Euclid detections and do phosphotometry for those sources on Rubin images. And then on the Rubin side, there'll be a group doing the other things, so to start from the Rubin sources and do phosphotometry on the Euclid images. So on the Euclid side, the way it works, so we take, so this derived data product DDP groups are kind of in between the collaborations. protect this the science. So for instance, for the DDP2 from the Euclid side, we'll have, so from the Euclid side, we have the list of sources, detected sources with position, flux, and morphology. And then the Rubin collaboration will share the coadded images, and we'll do phosphotometry on that. And then we'll share the phosphotometry catalog to the Euclid collaboration. But the Euclid collaboration won't see the Rubin images. And so we have split the work in between our two groups. So the group in there's a group in Munich led by Joe Moore, who will work and develop and adapt the Euclid photometric pipeline to do this task. And then there's a group in Paris, or in France, led by Simona, and where we do a realistic Rubin simulation of Rubin coads based on Euclid maps. And so the goal of those simulation is to validate the pipeline, and also it can be be useful for a much wider range of science. And then the two groups will split, will work and validate the pipeline and run the actual processing. So here, just a small slide, one slide advertising what is done in Germany to develop the photometric pipeline. So they've been working so far on the Rubin BP1 data, the EDFS field. So just starting to have things running, to like having ingest a buffer, a scheme, and to adapt the Euclid pipeline, extract what's necessary and work on that. And they do also do like simple tests, like you take the Euclid image and you degrade it to the Rubin staying, and then you do phosphotometry on that, and you see if you recover. It's like a sanity check, but so far it works mostly, so it's great. Kind of good precision. Yeah, and then in the remaining time, so what I've been working on simulating the coads. So the idea is to generate Rubin coads with Euclid maps. First goal is to validate the photometric pipeline we're developing, but also can be useful for a wide range of science. So we'll start to do one field in Cosmos and maybe other fields if we can. And so the way it works, so we start from the Euclid mocks, so from the flagship 2 simulations. So there's this mocks called True Universe. And those mocks have been used also in the simulate Euclid images. And then I'll generate Rubin row exposures using the IMSIM Rubin tool. But the key point is that in that I will tweak that to model the spectra and the galaxy spectral morphology in the same way it is done in the Euclid pipeline, so that we have a consistent set of images at the end between Euclid and Rubin. So be appropriate. So for that, and then we'll just run those raw images through the Rubin processing pipeline to obtain coads that will be in the very same format as the actual coads we'll receive. And so for all of that, I've been Jim Chung somewhere here. I've been of great help to help me go through this. And just to illustrate, so everything is preliminary, but still I started to play around just to generate on a tiny field in Cosmos, some simulation exists to see that at least all steps are running. And so I could just select CCDs from the simulations from the baseline, from Rubin simulations, which CCD overlap my tiny region. And I just select enough of those to mimic what's expected to be like in a year one, like 30 bands, 30 exposures. And then you can just run through that and generate coads. So here, just when it jumps together, you can see the image here on the Alliance image. So yeah, things are moving forward here. And this last conclusion slide. Oh, it's here. Yeah, so just to say, so this derived data product, so just to introduce you to this derived data product framework, which is used to share data between the two collaborations. So we're working this DTP2, the number product, which is to perform the phosphotometry and the Rubin coads for Euclid sources. And yeah, that's all.
Questions? Also online? So it seems everything was super clear. Thank you very much.
Let's move to the next one.
So yeah, we can move to the next speaker, which is sit here.
Yeah.
Okay, let's talk about other synergies.
Again, it's still me. So this time, it's talk about another another large experiment, which is this DAISY Run 2, which will happen in 2 years or 6 years, and specifically a sub-survey part of it, which is the IZ Dark Energy Survey, which will look at limit alpha emitters and limit break galaxies, redshift 2 or 3. Okay, so here, just to put in context, it's a small sketch of the current stage of experiments I could put together. So I highlight this. So DAISY is highlighted in red, in stage 4. So just there's been change in naming, so you may encounter those. So now DAISY, what you know as DAISY, may appear as DAISY Run 1. So what we call the extension of DAISY, which has started since this spring, is called DAISY Run B. And the DAISY 2, previously, what was previously DAISY 2 is now DAISY Run 2. So, yeah. So this is all using the same instrument, which is a DAISY instrument. So it's a telescope in Arizona, in the Mayo telescope. And then, so it has a large field of view, and the key part of DAISY is like that is 5,000 fiber positioners. So which allow to have like 5,000 spectra in one shot. So the throughput is pretty high, is very high, thanks to a thorough dedicated work of all the engineers for each part of the instrument. And in the end, you end up with a redshift factor, which is about 20 times faster than SDSS, or even more. So I don't describe the DAISY experiment. So basically, but the goal is to obtain like tens of millions of spectra to do bioacoustic oscillations, primarily to constrain dark energy. You have heard about it. But I'll talk about the DAISY Run 2. So the second phase of the experiment. So the idea is to keep the same instrument. So maybe some minor upgrades, but nothing major. And there will be different surveys in this. So you can see the footprint here. So what I'll talk a bit more after is the IZ Dark Energy 1, which will look at 4 million, which will gather 4 million spec redshifts over 5,000 square degrees. So you can see it's got the equatorial footprint in bluish here in two parts. And then you have what we call the cosmic growth, which will gather like about 50 million redshift at below redshift 1, so high density 1, on a larger footprint of 12,000 square degrees. You can see in orange here. Then dark matter, which will collect spectra of lots of stars. And then also a dedicated part for the Rubin synergies. So mainly it will be focused on the Cosmos and XMM-LSS, which can see 2 stars here. And so I just highlighting. So there's been a lot of development recently to how to coordinate between the two experiments. Because I didn't precise after, but DAISY for at least the high Z dark energy in the cosmic growth in the southern part, it will use partially Rubin imaging to do target selection. So that way, DAISY benefits from Rubin. And then there's been a lot of thought to how Rubin could benefit from DAISY. So the discussion, but DAISY can obtain thousands of spectra for many things for Rubin. So for instance, there's all life transient. So for all supernova or transient, DAISY can obtain spectra. So if you have see here, for instance, the spectrum of supernovae, and it has been all in a DAISY operation. It's implemented now to have alerts to observe targets of opportunity based on Rubin alerts. Then also DAISY can observe thousands of spectra for photometrically variable sources like AGN. So we can have a large timeline of several years here, and also for Messier science. And then also for all the weak lensing science, DAISY can obtain spectra for faint target to calibrate all the photometric redshift fundamentally. And it has been demonstrated, for instance, that it can have a pretty high success rate even for reasonably faint sources. So this is promising. And then there's even more, lots of different sense cases where DAISY can bring useful data to the Rubin sense, like for galaxy clusters or IGM or lenses, I guess. Okay, so now I just talk about IZ dark energy survey. So this will look, so you can see the footprint highlighted here in red. So the goal here is to gather 4 million redshifts, spectroscopic redshifts between redshift 2 and 3.5, roughly. So the idea is that DAISY with run and run-B, so with extension, will have extracted mostly all of the BAO information at redshift below 1.6. And so that's one of the reasons to go to higher redshift, because if you go to higher redshift with the instrument, so we have demonstrated that we can use those new tracers, Lyman alpha emitters and Lyman break galaxies. And so we obtain a lot of thousands of those spectra of such galaxies for dot observations. And now that we cannot probe the universe in this, we demonstrated you can probe the universe in this redshift range. It shows that we can access a lot of new information there. So here's a sketch. There are two reasons for that. It's because the volume there, cosmological volume, is huge. You can see on the sketch and just here on the right where it's kind of the volume scales with the number of modes that are accessible. So blue is the ZSS, orange is DAISY, and red is like a DAISY 2 or SPECS 5. So you have a lot of information there. And also the nice thing is that you can access to all the information there. It's less processed, but all astrophysical things. So you are closer to inflation there. So you can have more information of what all the inflation things. So the goal, and so we can constrain dark energy, cost of structure, or also inflation. So science driver is to tighten the constraints of BAO acoustic oscillation, so BAOs at those redshifts, where DAISY so far does not constrain much. We only have quasars that have pretty low density. We can also improve the constraint of redshift from redshift space distortion there, from cost of structure. And the exciting thing is that you can go also probe a new physics there, what we call fundamental physics or pyramidal physics. So we can because you can probe the universe at much you can you can measure your power spectrum that will measure with high precision there will be which have lots of modes closer to the initial conditions. So the primary thing we can constrain there is primordial non-Gaussianity, this FNL parameter, but there's also a lot inflation-related science constraints there. So to do that, we'll use two tracers, the Lyman alpha emitters, which are basically low mass star-forming galaxies with a strong Lyman alpha line. So you can see spectrum here with a Lyman alpha line around wavelength of 5,000 angstrom. And so we select those with dedicated medium band imaging. So basically, it's like you can see here the medium bands on the right. It's like your G band that you slice in 5 bands. So you can get much finer information. It's pretty efficient. And this is, so there's ongoing imaging survey built for that. So using BCAM, CFHT, megacam and CFHT, or HSC and Subaru, the VST. And the second thing we'll use is Lyman break galaxies, so which are more massive star-forming galaxies, and where the flux bluewards of the Lyman forest is absorbed by neutral hydrogen. So it's another one where you can see all the nicely detection of continuum with all the absorption lines there. And for those, we'll use the Rubin imaging, so UGR imaging to select those, because you will select at those redshifts we're working on, they will be red in U-T, so you want deep U-band, and there Rubin is critical for that. And okay, so yeah, sorry, hope some time, and so that's my conclusion. So DAISY, the first phase of DAISY is finished, this spring, and now the extension, so this DAISY run-B is ongoing and will end in a few years. And the next phase will use the same instrument, DAISY2, have different surveys, and lots of synergies with Rubin. And yeah, and it's in particular for the IZ survey, we'll use Rubin for just like LBGs. So, if you have any questions, let me know.
Thank you very much. Many questions this time.
Thank you. I was just wondering how much synergy is there between DESI Run 1 and DESI Run 2? Because if you're looking at photometrically variable sources and you're just looking at the Rubin fields, you don't really get those from DESI Run 1. So I was wondering just how much synergy there is there.
Sorry, can you repeat?
I was wondering how much synergy there is between DESI Run 1 and the predicted field for DESI Run 2. Like how much overlap is there between those two?
So the footprint do somewhat overlap. I've not put the DESI footprint here, but it's yeah. But we won't observe the same objects basically. So the footprint is here on the in this box here. But we won't observe the same object mostly, I guess.
Okay, thank you.
Hi, this is Ian Sullivan with Rubin Alert Production, and I was interested in your comment about the DESI follow-up of Rubin Alerts. In particular, what you are looking for in an alert that would signal that it would be worth following up with DESI.
So this, I don't know the detail. I just know that we have, so yeah, there are people already doing that, but with selecting, I guess, Rubin Pro generates alerts every night. So there's some selects here. I don't know which one are selected, but we select those and we add those. And so where we do observe during a night, they get spare fiber.
Do you know if any of those follow-up observations have been done so far?
Yeah, so those are implemented routinely in operation since I don't know, since 3 months, I guess. Yeah, probably you can see this paper from vendor or April 2006.
There was a question back here first.
Thank you. This is Henao Miyatake from Nagoya University. So, is it on? Okay, great. So my question is, so MAST and the WSD will start, well, at the same time as DESI2. And so what are their strategy and how does it align with DESI2?
Yeah, so we'll, so I'm not sure timeline. Yeah, MAST will be on the same timeline, you think? Okay.
MAST starts like around the same time
okay.
as DESI2, and WSD
so
starts like 2033.
I don't know. So yeah, so at least for DESI, so we have demonstrated we have the spectra. We have shown that we can do that with the instrument is working. So I guess we are somewhat in advance to that.
Sure.
To them in that sense. I don't know what the footprint of MAST will be.
Okay.
Maybe, yeah, I don't know what imaging they will use.
Okay.
And for WST, sorry, I don't know what's the same case there.
Okay, I'm going to cheat. Hi, Anand. This is Bob Blum of Rubin Observatory. I did think of a question for your first talk. How much overlap is there in the DP2 COAD and the Euclid DR1?
Not much.
So
yeah,
so
I did look at this because you have this nice eclipse.
Right. But we'll at least have the Euclid Deep Field South to start working on.
Yeah, so there is Cosmos.
Yeah.
Cosmos is there, Euclid Deep Field South, and I think the EDFS yeah, and I think this one also should be there.
Great. And the question, not a question, a comment on DESI. This is, I think, a tremendous opportunity for both communities, but it'll take some real input from the Rubin community. And so we'll look forward to hearing from folks about how they think they might be able to take advantage of such an opportunity if it arises. We definitely want to hear from the Rubin community about this synergistic opportunity.
Let's thank the speaker again. Next speaker is remote.
Yes, hello, everyone.
Hi, Hlam. Do you want to share the screen or prefer us
Yes.
to go?
Yes,
Okay,
I
go
can share. But I guess I have this message. You cannot start a screen share while the other participant is sharing.
We
Please.
can.
Okay, thank you.
Are you able to share?
Yes, now it's okay?
Yes, it's coming.
Okay, thank you.
Yes, thank you very much. Please go ahead.
Okay. Hello, everyone. I'm speaking from UK at midnight. I'm Elham, a research fellow at Southampton University. I'll talk about the LSST Vista fusion pipeline. This work was done with Manda Banerjee, Richard McMahon, and Raphael Shirley, part of the LSST UK project. Vista is a wide-field near-infrared survey telescope at Paranal Observatory in Chile. It observes the southern sky, so it has a strong overlap with LSST. Its camera VIRCam provides Z, Y, J, H, and KS imaging, which is highly complementary to the optical LSST bands. This extended wavelength coverage helps constrain dust, improve stellar mass estimates, and support a more complete physical interpretation of galaxies. Vista provides a rich legacy near-infrared dataset, including several surveys with different depths and science goals. Together, they offer broad coverage of southern sky from wide surveys to deeper fields. This plot shows how LSST and Vista complement each other across the spectrum. LSST covers the optical sky in 6 bands, while Vista extends this view into the near-infrared out to about 2.5 microns. Together, this broad wavelength coverage gives us a more complete view of astronomical sources and allows their properties to be measured more reliably than with optical data alone. The LSST pipelines are flexible, so they can also process data from other telescopes with that. For example, for Vista, we use the LSST pipelines. The raw images are first reduced by CASO pipeline. Then we use 2 public repositories, OpsVista and LSST-IR Fusion. Together, they allow VIRCam data to be processed inside the LSST framework. From this, we produce calibrated images, coads, and multiband catalogs in both optical and near-infrared bands. Before applying this to LSST, we first tested the pipeline with HSC data. HSC is a good test case because it is already processed by LSST-style pipelines. Here, we focused on the XMM field, where HSC overlaps with deep Vista video data. We produced deep coadded images and force photometry catalogs in a common framework. These XMM products are now hosted at the UK data center. This is an example of science enabled by LSST Vista Fusion pipeline. This work was done by my collaborator, Dr. Shenli Tang, using our HSC and Vista data products. Here, Here, a galaxy hosting and AGN at redshift 0.47 is analyzed in both optical and near-infrared bands. After removing the central point source, the host galaxy becomes much clearer. This shows that our pipeline products are good enough for image-based studies of AGN host galaxies. It also shows the value of combining optical and near-infrared data. The optical bands show one part of the galaxy, while the near-infrared bands trace the older stars that contain most of the stellar mass. After the HLC test, we moved to the Rubin DP1. Here we selected extended Chandra Deep Field South. The reason is that ECDFS overlaps with video CDFS of VISTA, which gives us deep VISTA data in 5 bands. For this run, we used the LSST sky map. We also kept the setup close to DP1 by using the same LSST version and matching the processing environment and configurations. And one of the important parts of this work was building the reference catalog for astrometric and photometric calibration. For this, we started from Monster, which is the general reference catalog prepared by the Rubin team. Monster is already well calibrated for the COMCAM optical bands, but it does not include the VISTA near-infrared bands. So in this work, I extended Monster into the near-infrared for VISTA data. For Z and Y, I followed the same method used by the Rubin DM team. And for J, H, and KS band, I use a strong cross-match with the VISTA public catalogs to add those bands to the reference framework. To check the quality of final products, we looked at both astrometry and photometry. In the astrometry plot, the DP1 positions accurately well with Gaia DR3. The robust scatter is about 0.08 arcsecond, and the bulk offset is only around 0.02 arcsecond, much smaller than a pixel. In the photometry plot, we compare our pipeline measurements with the video public catalog. Because the aperture definitions are not exactly the same, we first remove a small constant stellar offset around 0.1 magnitude. After that, the residuals are centered close to 0 over most of the magnitude range. The solid line shows the running median, and the dashed lines show the scatter. This slide shows a simple science check using optical near IR colors in the DP1 ECDFS data. On the left, I show the G minus I versus J minus K plane for our sources. This already shows 2 main populations. Then following Baldry et al., we subtract an empirical stellar sequence. In the lower panel, this transformation makes the separation much clearer. Stars stay close to 0 while galaxies move to higher values. The panels on the right show the same idea from the Baldry et al. For comparison. So this result shows that our fused optical and near-infrared catalogs recover the expected color space structure. Okay. The LSST VISTA fusion pipeline supports a wide range of science cases, and the community can already use these data products alongside ongoing LSST work. This example shows why the near-infrared is so important. This object is a candidate galaxy at about redshift 7 from the video ECDFS sample. It is very faint in the optical COMCAM bands, but it is clearly visible in the VISTA near-infrared bands. At these redshifts, because the Lyman break shifts to very red wavelengths. So the galaxy becomes faint in the optical while it is detected more clearly in the near infrared. So the vista bands are essential for identifying these kind of objects. For DP2, we will first start with LIS area using both video and VL's deep data from Vista to validate the processing. But we will then repeat the workflow in extended Chandra DP South, where we can also compare the results with our DP1 analysis. And finally, we plan to extend diffusion to selected VHS overlaps. Thank you for your attention.
Questions? I had one question to get started, which was about when you're running the pipeline and you were showing the different morphologies across the infrared and the optical. So my understanding is that running the pipeline, it will assume that the morphology is the same, so then the differences come out in the residuals. So how much does that kind of affect your photometry, that challenge of assuming the same morphology across the different bands?
Because most, I guess, until now, we need to, honestly, we need to work on that with many sciences. But as we experience until now, for example, in this area, I guess the near infrared, using the LSST pipeline for near infrared, I guess this is very a good idea, and this works. But about the morphology of the all of galaxies, I'm not sure. I need to test more for that.
Cool. Thank you. Any other questions? All right. If not, let's thank our speaker again. Thank you. Thank you. Next, we have Vincenzo Proteca to tell us about the VST survey to complement the Rubin. Okay. Oh, could you stop sharing, Elam?
Yes, I try, but I'm not sure.
Okay.
Now it's okay?
Still seems to be sharing.
Oh, one moment, please. I need to exit.
Okay.
All right, that's it. Thank you.
Okay. Well, thank you very much. Okay, hello everyone. So let's talk about synergies with another instrument, VST. The name is similar to Vista, but it's another machine. So VST is the VLT survey telescope. So why it is important to be synergized with LSST? Because you can imagine it as a small scaled down version of LSST. It has quite a wide field camera. It's 1 square degree, so a tenth of LSST, of course. It is a good image quality, and so with 1 hour exposure time, more or less, we can get exactly the same depth as LSST. So if we select a smaller region of sky, we can improve the LSST cadence to get high cadence transients. We have the same pixel scale LSST, similar photometric system, UGR, INZ, SDSS, plus H alpha, and also a polarimeter that will be installed at the end of this year. And the location is in Chile, so very similar to LSST. And the VST is the core of 4 Italian in-kind contributions, as you can see here in the list, but I will focus on this one in particular. So this is our team. The PI is Maria Teresa Botticella, and our core team is mostly based in Napoli, as you can see from the Vesuvius here in the logo, but there are also collaborators in Padova. So the core of the in-kind are transient, so the main recipients are the TVS and the desk time domain working group. So we also have a website that we are updating with information, so please go ahead and check if you want to know more. So the idea is that we want to observe in synergy with LSST one specific small region within one of the DDF. And at the beginning, we decided to focus on EDFS. And the reason is that we already discussed before, it's important for synergies with Euclid and in future also with Roman. And it was the only DDF that was not yet observed by VST, as I will show at the end of the talk. So what we plan to do is that we will observe 80 nights per year from 2026 up to 2032. And the deliverables are coded and calibrated images, source catalogs, and also light curve of transients that we plan to release as soon as possible together with LSST, so you can enrich the light curves. So why EDFS? We already discussed, so I think I can go very fast on it. There is a specific MOU between Rubin and Euclid on this field, so data will be immediately available between both communities, and there is also a plan for the derived data products, and Roman will observe the same field. So having both surveys together will allow you to have both increased accuracy on the property of the host galaxies and also light crystal transient that can extend from the U band up to the near infrared. And so the problem is that yes, this field is double the size of a normal DDF, the cadence is a bit shallower, and so we propose to increase this cadence with VST. So before the start of our in-kind in 2026, we designed a pilot project for the in-kind, which is the survey VESTA, which stands for VST Euclid Synergies for time domain astronomy. And we use it as a pilot survey because we designed to observe 4 square degrees in the central part of the Euclid field south, as you can see in this picture. And this is because Euclid already observed this field about 10 times, which is part of the data release 1, which will become publicly available in November this year. And so our aim were to build joint light curves from space and ground as a test base of what we could do in the future with Rubin plus Euclid, and of course, adding also VST. So we are preparing deep reference images that we can use for our in-kind, and we are doing a pipeline test for the data reduction, the transient search, the homogenization, and also the delivery in preparation for the in-kind. And finally, what we plan to do now that DP2 is out is to do cross-calibration between VST and Rubin DP2 images, also using static sources so that you can ensure that the photometry of joint light curves is consistent. So we observed this field from October 2024 to December 2025 with a weekly cadence alternating couples of GR and RI bands with 4 square degrees. So what we are doing is that we developed an end-to-end reduction pipeline that is doing the basic data reduction, and then we have a transient pipeline called HSPRITS. We are kind of replicating what the alert production pipeline for LSST is doing. You can see here an example of the coded image that we use as a template and the subtracted image in the R band. So with our pipeline, we do also candidate identification, real bogus separation, and the candidate ranking to separate the promising ones from the possible boguses. And finally, we produce light curves. I can show you a few preliminary examples here. You see 2 examples of possible supernova candidate. In the first 3 panels here, you can see respectively the difference image, the search image, the difference image, and the reference image. Here you see other examples of difference images using a search image, this other one before, and this is another example for another source, and you see also the preliminary data. This is in the R band, and we also have other examples. So far, we detected around 100 possible supernova candidates with this preliminary search. And I also have one thing to show you. This is very, very preliminary, so take this plot with some caution, but this is a first taste of what we will have soon when both Rubin and Euclid will be fully operational, because this is a light curve of a supernova using both BST observations in G, R, and I bands and Euclid observations. You see these late points here. So this is just the beginning of what we could have in the future once all the surveys will be fully operational. But we don't have only transients. Albeit transients are the main focus of the in-kinds. We are detecting other possible variables. So we will build a source table of these catalogs to be delivered. So it can be a science product for all the science collaborations, not only TVS and DESC. So as a concluding remark, I want to say that VST can be an excellent support machine for LSST. Albeit it's a small scaled down version. Our in-kind team is producing a pipeline which is similar to the LSST ALET production one. And this is because we will soon start releasing the first photometry of all the LSST discovered transient in the central region of EDFS. So our idea is that we start releasing this around autumn 2026. All the information are on the website that I showed at the beginning of the slide. We will use a data center based in Napoli, and you can request credentials to get these light curves. And this field is very important because it will be a key region in the future with multi-wavelength coverage, and VST can help obtaining high cadence light curves on this field. But before to conclude, I also want to mention another in-kind of the four that I was mentioning, in which I'm also involved, and this is an in-kind that is going towards the end, and it observed the other deep drilling fields, so Cosmos, ELISA, XFMM, and CDFS, to build long light curves of possible AGN candidates. As you can see here, there's still 4 square degrees in all the fields, and we also started doing some cross-match between the VST observations and the LSST DP1 observations. So in the end, we can also have up to 12 years baseline for AGN, which is extremely important. Of course, we have big gaps, but this is important to have early signs with AGN because, as you know, the typical red noise trend requires very long baseline to distinguish them from transients. So all the information are on this website as well. Thank you very much.
Sure. When you're making the pipeline, were you able to use the training sets for real bogus and translate a lot of those things, or did you have to make custom classifiers for the different data set?
I think we could try to use it. So at the moment, we are using many different modules together. So as a first thing, there's a machine learning algorithm. It's just a random forest based on the images that we produced some time ago. Then we have some ranking that we do with the parameters after the source extraction. And as a final step, we have visual vetting. So in principle, we could try to use the same approach with multiple data coming from different surveys. We used it only for Euclid and BST separately. We still have to try to use it on both surveys together.
Yeah.
Hi, this is Shreya Anand, postdoc at Stanford. Do you have an estimate for the rates of transients of different subclasses that you would detect with Vesta and Rubin in these?
An estimate of the
rate, or like how many numbers?
No, I don't have a clear answer so far. So I can only say that analyzing the first 6 months of this project with BST only, the number was about 100 for one of the supernova candidates, more or less.
Last questions? No, let's thank our speaker again. So we have Ryan Olkers.
Okay, good afternoon, everybody. My name's Ryan. I come from the University of Texas, Rio Grande Valley. If you know anything about UTRGV, it's in Brownsville, Texas, which has a nice median temperature of about 100 degrees Fahrenheit these days. So if that doesn't sound appealing, we also have humidity that's usually in the high 90s. So coming to California these days is a real treat. But I won't talk to you about the weather anymore. I want to talk to you about a new survey that's coming online in the next couple months called Toros, and how we expect to synergize with what's going on in Rubin LSST. So I don't think I need to convince anyone in this room that Rubin LSST is really going to be pushing astronomy forward, both in understanding how we can do large-scale data reductions, but also just astrophysics in general. But it's important to remember that we have a lot of very small to medium-sized telescopes that can still be used as support large astrophysical resources and telescopes, such as Rubin LSST. I like to describe myself as sort of a recovering exoplanet person. And if you know anything about how exoplanet science worked, once TESS came online, we had a lot of telescopes that we had to repurpose in order to support TESS. And so I'm going to talk to you today about how we're trying to use smaller telescopes. When I say this, I mean like 1 to 2 meters in diameter and size and smaller. So Toros is a collaboration of a couple of Texas universities, as well as a couple of universities in Argentina. We've done a lot of work providing rapid response photometric follow-up for LBK sources over the past 10 years or so. And we now want to try to pivot to try to do some bright follow-up of Rubin LSST sources. The final location of the Toros telescopes are going to be at this observatory in Argentina called Felix Aguilar, which is actually just on the other side of the mountains, basically, a Rubin LSST. So we have a very good latitude placement. This is an image of the observatory itself. The observatory has very good sky brightness down to about V of 21.5 or so. We anticipate we get about 8 hours of clear night per day on average, which is assuming sort of a poor weather model of 75%. But in general, most months there are closer to about 90-95% weather. So it's a very good site, even if it's sort of a smaller observatory. There's 2 telescopes that we use. So to quickly describe the instrumentation, the first one is Toros YY. It has this nice name because it used to be known as the Yale Double Astrograph. Did a lot of work using photometric plates and then eventually CCDs to do astrometric follow-up of a variety of sources. We repurposed it in 2024 for the Toros survey, and we're working to get it to be fully robotic thanks to funding from the Mount Cuba Astronomical Society. So this telescope is equipped with a 10K by 10K monolithic CCD, which has about 1.5 square field of view. So we're able to do sort of wide field tiling of the sky. So far, we've shown that we got down to about 21.5 in G in about 5 minutes. The second telescope is called Toros PW. So we have these great acronyms. This stands for Toros Plane Wave. This telescope was originally supposed to be set up in a very far out there facility in Tolo Grande, Argentina, but we moved it down to Felix Aguilar for simplicity. This telescope has instrumentation that will have a CMOS detector with a UGRIZ filter wheel, and will also be fully robotic. So we're able to do much more targeted follow-up, color follow-up with this telescope. Has a smaller field of view, about 7 by 7 arc minutes, a little smaller or so. So we have the nice plot which shows sort of how the pipeline works. It makes your eyes bleed. But the important thing to know is that we have a listener that takes information from a variety of brokers. In this case, what we do is very targeted follow-up from brokers. So we're listening for specific objects to flare up in some way. That updates our field plan, which then updates our database and tells things like how the hardware pipeline will work to move the telescopes to a variety of sources. And then it does automatic post-processing of the images and then stores them. Our ultimate goal then is to put them on a visualization portal that folks can then use to look at specific targets. So all the data that from Toros will be publicly available. This is our first light image of the SMC that was taken a couple years ago. It looks very nice. The precision capabilities of Toros YY, we're very happy with the progress so far. So although we're not reaching the photon limit, we actually are passing what we anticipate the sky and the photon limit together to be in the noise, particularly on the faint end, which is good. It means we can follow up some of the fainter sources. We have onset of saturation around G magnitude of 10 or so, and the sky really starts to dominate around 17th. Our precision floor is about 0.5%, which is good for the bright sources and also we're pretty encouraged because of how faint we get on the faint end. So I wanted to talk a little bit about commissioning, and this also actually leans into how our synergy with LSST. So these were 3 fields that we did commissioning for in late 2024. They were selected primarily to test various aspects of the system. Could we detect transients in galaxies? Could we do good subtractions in crowded fields, et cetera? Serendipitously, the 47 tuck field, we selected this without realizing it, actually lines up quite well with the DP1 field. So you'll see some results from that comparison in a minute. So our difference imaging quality is quite good. We've done a lot of testing on the pipeline that we've been using, and it seems to work well on most of the telescopes that we've used it on, and Taurus is no exception. So as you can see, galaxies are subtracting quite cleanly. The residuals are having a noise level that we expect. We are not anticipating initially doing searches for transient because we want to try to do specific targeted follow-up of various objects. But we do have a graduate student who's working on trying to get our automatic transient detections working. And so far, it seems to be working for things like supernova, and we're also recovering variabilities that we would expect that are very similar to other surveys, which is good. We have a variety of ways to automatically detect variability that we've used for various surveys before. I label some of them here. All of this information will actually be included in the catalogs that we release. So we have variability indexes, we have understandings of what amplitudes are, periodicities, false alarm probabilities, et cetera. And as you can see, we have a variety of variables which we've been able to recover. So we have long-term variability, we have outbursting things like CVs, we've been able to recover rotation periods of things like CVs, and pulsation periods of things like RLRI, which is nice. And then we've also found some more exotic things, which are eclipses that could be occurring in variable type objects. So we're pretty excited about the capabilities of the system, particularly because one of the telescopes is a repurposed older telescope. So how do we expect to synergize with LSST? Well, again, we have very specific science goals in UTRGV and Texas A&M and at the Argentinian institution. So we are selecting specific science targets and then having the alert brokers tell us when these types of objects could be flaring or going off in some way. And that then triggers both telescopes to observe them so that they can get color follow-up and wide field follow-up at the same time. But then the goal is once that information has taken, we then release that data to the public. So typically the first question I get when talking about smaller telescopes like half meter or meter in size is how can you actually reasonably follow up Rubin LSST things because your telescope is so small. So it turns out that a single exposure for Rubin LSST is roughly close to the same in signal to noise for a single exposure from Taurus. They are doing much faster observations and we are doing 5-minute observations, but it still gets us within a ballpark where we should be able to make a pretty good observation of the source that we're looking for, at least for follow-up potential and giving it some initial color observations, which is nice. We've already been tracking some objects and we've shown that we will be able to show variability that is similar in both the Taurus light curves and the Rubin LSST light curve. So some of the data you're seeing is from DP1. We've already done work as well to get very rough 0 points between the two systems. So we're hoping that this will see sort of be a very quick process once everything comes online. And I'm not sure what just happened. Okay, then I will just put up my summary slide here, which talks about basically the expectations for the system. Again, we're still working on getting everything robotic, but we expect that to be finished within the next 6 months or so. And we were hoping that we can provide very good follow-up for a variety of LSST sources that are targeted right now. And any data that is released should be public. We're planning our first release with the commissioning data from Taurus this fall. So please look out for that, and I'll be happy to take any questions.
Questions.
I saw that one of your right. Okay, I saw that one of your science cases is CVs. How crowded can you? How crowded fields can you observe, and like have your DIA pipeline safely recover your object?
Yeah, I wish I had a picture of it. So from 47 Tuckfield, at least, we do get quite deep into the cluster and recover a lot of the variability. I don't have the number for you, so I don't want to say it off the top of my head, but we're pretty happy with how far into that cluster we're able to recover variability. And so those, I know what the picture looks like in my head, and so I'm trying to think it, but it's pretty deep into the center. So we're pretty happy with it.
I had one question, which was, would you consider kind of prioritizing Rubin transients when they're at peak and have actually saturated in Rubin? So that's where like a smaller telescope would really help complement the Rubin.
Yeah, I mean, that's sort of our goal. Right now, to sort of simplify getting online, we've decided to sort of prioritize the targets that we think we're going to be matching well with some of the science cases we had originally done. But once everything is running smoothly and we're sure that the telescope is a full robot and sentient, I guess, we can add more to or we can widen what the broker will accept us to then go do follow-up for. So, yeah.
Cool. All right, there are other questions. Let's thank our speaker. Our last speaker is Miranda Zach.
Hello, my name is Miranda Zach. I'm a grad student at Penn State. I'm working with Charlotte Ward, and I'm talking about maybe a more niche thing now. We're getting into changing look AGN. So I'm going to be talking about how we aim to detect changing look AGN and/or the underlying accretion disk instabilities, specifically with multi-survey photometry. So just as a speed review, if you're a little unfamiliar with changing look AGN, they exhibit relatively quick changes in broad optical emission lines. I say relatively quick, and I realize that for a lot of transient science cases, it's really, really slow, like timescales of months and years. But in AGN years, this is fast. So changing look AGN are traditionally identified through their spectra, through the appearance or disappearance of these broad lines, but they can also be detected pretty reliably through photometry alone, just based on atypical and behavioral changes in the light curves. So Rubin, because we'll be producing millions of AGN light curves, so it will be extremely valuable in changing look AGN studies. I don't need to convince anyone of Rubin's value, but it's going to be a little bit trickier than doing spectral detection of changing look AGN, because there are so many different ways that the accompanying photometry can look for changing look events. So I have, excuse my crudely drawn light curves, but these are a few different examples of what changing look events could look like in AGN light curves. One example is there's just a flux offset in a light curve, whether it increases or decreases, could go either way. There's another case, and usually these are not independent. Usually there are combinations of these different signatures, but another case where we see maybe it starts with low variability and it moves to extreme variability, or vice versa. And then sometimes we just see just interesting flares in AGN light curves that also represent change in look events, and sometimes combinations of multiple of these. So being able to identify such a wide variety of these types of events is tricky, even with the great bounty of light curves we'll get from Rubin. So two main goals for these light curves. One, I guess the broadly underneath all of this is just to better understand changing look AGN and why they're doing what they're doing, what the underlying physical mechanisms are. We really want to identify new changing look AGN, because growing our sample is just going to help us hugely in understanding more about them, and also eventually inferring physical properties about the changing look AGN from the time series data itself, because these light curves are exhibiting all sorts of different signatures, and from these signatures we can understand things. We hope to understand things about the physical processes that are happening to create those signatures. So I'm arguing the best approach to do this is combining data from multiple surveys, not just Rubin. primarily because longer baselines are really, really critical for detecting change in look AGN. Rubin hasn't been around that long, so we don't have that much time to work with in terms of detecting change in look events. So using data from prior surveys is really, really almost necessary to do a good sweep of change in look events. Combining different cadences or sampling patterns between surveys will also help us establish more reliable analysis of variability because we're reducing potential for bias from sampling patterns and potential bias from survey calibration for combining multiple surveys. Also, if we're combining surveys with multiple wavelengths, we get the opportunity to probe different emission regions of AGN, and different depths will allow us to analyze a wider variety of AGN luminosities, of which there are a lot. So to start this, we should start with realistic simulations if we're going to build a classifier for change in look AGN. I don't know if anybody from Light Curve Links is here. There, I think I saw Alex Knowles wandering around, but accidentally talked. I did not develop Light Curve Links. I'm just a user, but I am a proud user. Light Curve Links is very cool. It's a package you can use to simulate light curves for a variety of science cases, and also after simulating the data, using the same package to then sample the data with a variety of survey patterns. So it's really helpful for like combining everything in a clean way. Also, EasyTauX, an AGN light curve modeling package using Gaussian processes, is actually can be wrapped into Light Curve Links. So combining these two, we can generate some pretty cool multi-survey simulations of light curves for AGN. Even though these aren't technically like fully realistic light curves, because we don't have a complete definitive physical model for what is creating the change in look events. And we don't even know if, it's probably not one that describes all change in look events in the first place. So ideally in the future, we'll have these based on physical models. For now, we're mainly sticking to like damped random walk changes, things like that. This is an example of a multi-survey simulated AGN light curve. This is not a change in look AGN simulation, just the regular one. But we can see from it how much the simulated ZTF data adds to our understanding of this light curve. So this is ranging from 2018-ish to present day-ish, ranging into the future to like 2035, 2036. So we can compare between the simulated ZTF data and the Rubin data to see how much, first of all, how much longer our temporal baseline is, how much this will help us in detecting change in look events, to how different the two surveys are in the sort of like precision of variability that they can detect, and also comparing cadences between surveys. We can get an idea from these simulations what kind of surveys we should be using to look for different timescales of variability in AGN. So just a quick example, and then also just of Rubin simulated data, we can look at an example of a changing look AGN light curve. This is because there's not like a established way to simulate changing look AGN events at this point. This is just two damped random walks stitched together with a short transition period in between them. So we can see on the left here, we have different parameters for the time scale of variability and the amplitude of variability going to the next light curve. So hopefully using these simulated data for lots of different surveys for change in look AGN will help us train these classifiers to then use on real survey data and identify change in look AGN. I will leave with a couple points. We know that Rubin is going to do awesome things for the change in look AGN studies, but we also know that data from additional surveys is really going to be critical to identifying more and understanding what's really happening. And in the future, we're excited to establish more physical models and use some simulation-based inference to extract physical parameters from light curves. If you have any questions, thank you.
Any questions? Close to 5 p.m. So let everyone head out.
You can come talk to me later.
Yeah, that was a question.
Oh, I should introduce myself, Katarzyna Kruszyńska. So I have a question. You show the ZTF and LSST light curve. Are there any other surveys that you identified as good?
Yeah, so simulating like future Roman survey will also be cool. There's probably like WISE surveys will be beneficial. Like this is all with light curve links. It's cool. You can add in your own survey parameters. So if you can think of it, even if it's an imaginary survey entirely, you can see what the light curve would look like with that sampling pattern and that like the flux limits and everything. So I anticipate ZTF, Roman, Rubin, but there probably are more that I'm not thinking of that would be good also.
I think the two we just heard about would be great.
I thank you for the talk. It's really interesting. So yeah, first thing I would like to advertise you again the VST products that I was mentioning before.
I was writing down
Because
notes.
they might be useful. I was telling 12 years is the total baseline, but actually for the last 2-3 years is continuous baseline with 15 days cadence. So might be useful.
Okay.
And also as another question, have you considered doing this kind of work with the extended Stripe 82 data? For instance, both I and Weishang published recently works analyzing those data, and also Zach Stone a few years before using SDSS, PanStars, and ZTF, and also Gaia. So you have a very long light curve. We try to model either with DRW, DHO, or explicit PSD, so you could see if there is any difference from the ordinary variability from a list of sources.
Yeah, that'd be great. Thank you.
All right, I think we
Sorry, it's not a question, just a comment. I do want to add on that the reason why we are using, I work with Charlotte and Miranda. The reason why we are using ZTF and LSST and we haven't explored other ones is because they're the best like wide surveys that we've found so far that overlap. So a lot of the other surveys are very narrowed in our field of like finding these changing look AGN. So if we were to put this training set that Miranda's using to the test, it's kind of harder because we don't have as much overlap. So that's why we're training on it, I think.
This is true.
We're out now. Thank you everyone for coming.